Okay, sveiki Vilnių! Aš esu Aronson, T-Rexas iš Kodosaurus ir atskridau čia ant savo augintinių pterodaktilio, kad išmokinčiau jūs, kaip reikia naikinti mutantus. Got a bit ahead of myself on the slides. Yeah, spoiled the surprise. Visgi, to jau esu pasakojama angliškai. Mainly because you've just heard almost all the Lithuanian I actually speak. I'm going to try and get us back closer to on schedule, talk a little fast. If you have trouble keeping up, please just go like that or something to tell me to slow your roll, okay? So, to start off, what on infinite Earths makes mutation testing different from all the other software testing techniques we know? Mainly, most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is correct, at least in the sense of passing its tests. Instead, mutation testing is checking for two other qualities. And I think in a typical code base, the more important one is that our test suite is strict. Now, you might think that's what code coverage is for, right? No. The only thing that test coverage tells us is that at least one test ran the code it claims is covered. It tells us nothing about whether the correctness of that code made any difference to whether a test passed or not. And isn't that what we really mean when we say code is tested? I think it is. So how can we actually tell? That is where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. When we find these gaps, we can close them by either adding more tests or by expanding and improving some existing tests. Lack of this strictness usually comes from lack of tests, of course, but also from poorly written tests. The other thing mutation testing checks for is that our code is what I call meaningful, so that any tiny little semantic change to the code will have a noticeable effect on the code's behavior. Lack of meaning usually comes from code being unreachable or redundant or just not having any real effect. When we find meaningless code, the usual fix is to just rip it out. Mutation testing puts these two together, yay, by checking that every tiny little semantic change it knows how to do does make a noticeable difference to the behavior of the code, and that our test suite is strict enough that at least one test will notice that change and fail. Now that's the positive side, but there are some drawbacks. As Fred Brooks told us back in 1986, there's no silver bullet. The first drawback is that it's hard labor on the CPU, and therefore rather slow. We certainly won't want to mutation test our entire code base every time we save a file. Maybe over a lunch break for a smaller system, or perhaps a weekend for a rather large one. Fortunately, most of the tools do include ways to tell them, just check this one function, or this class, this file, maybe a few files, whatever. And they often include some sort of incremental mode, so that we can tell them, just check what's changed since the last time we ran the tool, or the last git commit, or the changes from the main branch, or whatever. With filtering like that, we can we can maybe check at least just the relevant changes every time we save a file, or at the very least, just check it over a much shorter break than otherwise. Another drawback is that it's frequently not at all clear what we're supposed to do about the results. A mutation testing tool will tell us that some particular change to the code made no difference whatever to the test results. But what does that even mean? It takes a lot of interpretation to figure out what mutants are trying to tell us. They're usually trying to tell us that our code is meaningless or our tests are lax. But it can take a lot of time and effort to figure out exactly how. Even worse, sometimes it's a false alarm. because a mutant might not make any test fail, but that's often because it didn't really make a difference to the code in the first place. But it can still take a lot of time and effort to figure that out. Now that we've seen some pros and cons, what exactly does mutation testing do? It mutates copies of our code, hence the name. And it does this in order to create test failures, otherwise known as faults. So mutation testing can be categorized as a fault-based testing technique. And this means it's related to something you might already be familiar with, Chaos Monkey from Netflix. But the way mutation testing works is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their network metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects semantic changes, not necessarily problems. We hope that each of these changes will indeed create faults, but that's up to the test suite. It injects these changes into copies of our code, not our actual network, and it does this in our test environment, not production. And if all still goes well, in the sense that our tests all still pass, that doesn't mean all is well. That means that there is a problem. Remember, each change to our code should make at least one test fail. So how does mutation testing do all this? First, the tool breaks our code apart into pieces to test. Usually these are our functions, or if we're using object orientation, maybe they're methods, whatever. For simplicity, I'm just going to say functions. And then for each one, it makes a bunch of mutants from that function. And to do this, it looks closely to see how it can be changed. And for each tiny little way the tool sees to change it, the tool makes one mutant with that one mutation. And once our tool is done creating all the mutants it can from a given function, then it iterates over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. Most of them don't give us anywhere near this much information, let alone so neatly organized, but it's a useful conceptual model. For each mutant derived from a given function, the tool runs the function's tests, but it runs them using the current mutant instead of the original function. If any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the change that the tool made in order to create this mutant did have a noticeable effect on the code's behavior, and that our test suite is indeed strict enough that at least one test noticed that change and failed. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then the mutant is said to have survived. And that means that this mutant has the superpower of mimicry, skilled enough to fool our tests. That usually means that our code is meaningless or our tests are lax, or both, and now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code, you don't need to bother reading and understanding all that code, into this AST, which again, you don't need to bother understanding in full. Then it traverses that AST looking for subtrees, or branches if you will, that represent each function. And from each one, it makes mutants. To make mutants from an AST subtree, it traverses that little subtree, just like it did before to the whole thing. But now, instead of looking for even smaller subtrees it can extract, like twigs or something. It's looking for nodes where it can change something. And each time it finds one, then for each way it can change that node, it will make a copy of the function's AST subtree with just that one node changed in that one way. In other words, one mutant with that one mutation. Now I've been talking a lot about changing things, so what kind of changes are we talking about? There are quite a lot. You could change a mathematical, logical, bitwise, or whatever else you have, operator from one to another, including across those categories when the language allows. When the order of operands matters, it can swap them. You could change a comparison from one to another. It can remove an if condition or a looping condition. It could replace a function's entire contents with just returning some constant or one of the arguments or deliberately raising an error or nothing at all. It could change a value to some other value, even possibly to an incompatible type, like changing a number to a, if I may quote Smeagol, string or nothing. There are many more types of changes, but I trust you get the idea. Now, there are no more general low-level details I wish to add, so let's walk through some examples. We'll start with an easy one. Suppose we have a function like this. Never mind why, it just makes a good simple example, so let's roll with it. Think about what a mutant made from this might return, since that's probably what our tests are looking at. It doesn't look like it would have. Now, suppose we had only one test, like so. This is a rather poor test, and I think at least one reason why is clear to most of us. But even so, most of these mutants would get killed by this test, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason the tool put a 4 there as opposed to 0, 1, -1, and other such significant numbers. Changing the exponentiation into subtracting one argument from the other gets us 0, dividing them gets us 1, and the mismatched types and deliberate errors will at least make the tests not pass. But addition, multiplication, and exponentiation in the reverse order all get us the right answer. So mutants based on these mutations would survive our current test suite. That's the usual way that mutants survive, by returning the same value as the original function, or having the same side effects, whatever it is that our tests are looking at. To determine how that happens, for a given mutant, it helps to take a look at that mutant along with at least one of the tests it passes. So let's start with the plus mutant. Looking at this change together with our test makes it pretty clear that this one survives because 2 plus 2 equals 2 to the 2. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against the mutant that would pass when run against the original code. To do that, we need to make at least one test use inputs such that x plus y is different from x to the y. There's lots of ways we could do that, such as asserting that 2 to the 4th power is 16. All the tests, all the mutants that our original test killed, this would still kill. But also, 2 plus 4 is 6, not 16. So this kills the plus mutant. See how that works? Yeah, I'm seeing some nods there, good. Better yet though, 2 times 4 is 8, which is also not 16. So this kills the times mutant as well. Killing one mutant often kills many other mutants of the same function. But the pair of argument swapping mutants still survive, because 2 to the 4th and 4 squared are both 16. But we can attack them separately. No need to kill them all in one shot and be some kind of superhero about it. To kill these ones, again, we can either add a test or adjust our existing test to something like asserting that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills the argument swapping mutants. And better yet, 2 plus 3 is 5, 2 times 3 is 6. Both of those are not 8, so the times and plus mutants stay dead. We don't get any zombie mutants wandering around, even if this were still our one and only test, if we just adjusted the test rather than adding any more. With these inputs, the correct operation is the only one that gets us the right answer, at least the only simple common one. This isn't the only solution, though. There are lots of ways to skin that flurkin. Now, this may make mutation testing sound rather simple, but this was a downright trivial example. So let's look at a more complex one. Suppose we have a function like this to send a message. Send message uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping to pick up where it left off until the whole thing is sent, a very common sort of pattern. A mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. Now suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a little bit more that I'm not going to show you quite yet, dealing with setting the size and actually creating the message. But even without seeing that test code, what does the survival of this non-looping mutant tell us? If a mutant that only goes through this loop once acts the same as our normal code, as far as our tests can tell, that means our tests are only making our normal code go through that loop once. So what does that mean? You'll find that interpreting mutants often involves a lot of asking yourself, so what does that mean? Often deeply recursively. In this case, it means we're not testing sending a message larger than send bytes can handle in one chunk. And there are lots and lots of ways that could happen, but we're just going to look at 2 possibilities. The most likely is that we simply forgot or just didn't bother, though we really should have tested with a big enough message. For instance, suppose our maximum chunk size, what send bytes can handle in one chunk, is 10,000 bytes, but we're only testing with an itty-bitty 3-byte message. The obvious fix is to deliberately use a message larger than our maximum chunk size, and with this sort of pseudo messaging, we can easily construct one like so. But let's look at another possible cause and solution. Maybe we did test with the largest permissible message out of a predefined set of messages, or at least message sizes. For instance, here we have small and large message sizes, and we test with a large, and yet this mutant survives. In other words, we're still sending the message in one chunk. What could possibly be wrong with that? Sounds like a good thing to me. What is this mutant trying to tell us in this scenario? This time it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this, and if we keep tracking down what else might not be needed, because it was only there to support the looping, we wind up boiling it down to this. And now the ultimate message is quite clear. The entire send message function itself may be redundant, and we can just use send bytes directly. In real world code, not example code, there might be something like logging and error handling and so forth that we need to put in send message and we can't put down the stack into send bytes. But at the very least, it showed that the looping was redundant. Fortunately, when it's this kind of problem, the solution is clear and easy. We can just rip out the extra stuff that the mutant didn't have. And this will also make our code base more maintainable by getting rid of useless cruft that just gets in the way of understanding it. And for the security-minded among you, it might reduce its attack surface and all kinds of other cool benefits. Now that we've seen examples of finding both bad tests and redundant code, I'll address a couple frequently asked questions. First, this all sounds pretty weird, deliberately making tests fail to prove the code succeeds. Where did this whole bizarro idea come from? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 as part of Richard Lipton's term paper titled False Diagnosis of Computer Programs at Carnegie Mellon University. But the first tool didn't even appear until 1980 as part of Timothy Budd's PhD work at Yale. Even then, it wasn't practical on typical computers until about the early 2000s, with significant advances in CPU speed, multi-core CPUs, larger and cheaper memory, and so forth. Today, it's practical even on fairly low-end, but still modern systems like this 2020 MacBook Air. Another common question is, where should we fit this in our development process? Mainly, I think it belongs at least here as part of the requirements for a pull request or whatever your process uses to be approved. You can set some standards for what you're willing to tolerate on the changed code or the whole code base or whatever. And ideally, this would be enforced automatically as part of a CI pipeline. That would be started when the PR is created and block it if the criteria aren't met. That said, though, I would also personally do it here in the linting step as part of applying a whole suite of quality checking tools before I say, hey, comment on this code. You want it to be as good as it can be within reason before others get their eyes on it. And if you want to try mutation testing for yourself, here's a list of tools for some popular languages and platforms, including, of course, Python and some not so popular. I doubt many of you are doing Fortran 77 these days. Don't worry too much about pictures. The final slide contains the URL for the whole deck. You can take a picture of that one and get it all. And the tools that I know are outdated are crossed out in this list. I don't know or follow quite all those languages and tools, though. To summarize at last, mutation testing is a powerful tool to ensure that our code is meaningful and our tests are strict. It's easy to get started with, but it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean it might not be all that great a fit for our current projects right now, I still think it's just a really cool idea in a geeky kind of way. If you have any questions, I've used 23 of my 25 minutes. Plus, as promised, there's the URL for these slides and my contact info. So, anybody got some real quick questions? Okay, I guess we're back.